Hello, welcome to my first talk at NCNGT 2021. Um, I'll be giving two talks on this, and I'll be speaking about symplectic fillings and cobordisms of lens spaces. This is joint work with John Etnyre. So the plan for this is that the first talk will introduce the main result about the classification of symplectic fillings of lens spaces. And in the second talk, I'll introduce some research directions that we found interesting that stemmed from this project. We obtained some partial results there, but we think there's interesting things to look forward to. Then I'll try to introduce them in the second talk. So I'll assume the following background for all listeners of this talk. I've included the links in the description of the video. So what you'll need to know beforehand is the classification of tight contact structures on lens spaces. This was work done by Honda and Giroux independently in around 1999-2000, and Honda's paper is a very good resource for this. And the second thing you need to understand is the notion of symplectic fillings of contact structures, the different kinds of fillings you can have, namely strong, weak, or Stein. And a good resource to understand that is Burak Ozbachi's survey. I've included links to both in the description. So moving forward, so an overview, contact structures on three manifolds, on any contact manifold, broadly comes in these two flavors. They're either tight or over twisted. And under tight, you can have two flavors, which are fillable and non-fillable. So we are interested in fillings of contact manifolds. So we'll restrict our attention to fillable contact structures. And as I mentioned, fillings come in three flavors. You can have weak fillings, strong fillings, and Stein fillings of contact manifolds. Now, the notions overlap. For rational homology spheres, any weak filling can be perturbed to become a strong filling. And for manifolds that are supported by planar open books, any strong filling can be perturbed to actually give a Stein filling. So we are interested in lens spaces. Lens spaces admit planar open books. So all tight structures are Stein fillable, and all strong fillings can be perturbed to Stein fillings. This follows from the classification by Honda and Giroux, and then results by Gompf and Eliashberg of characterizing Stein domains, and then Wendel's work in perturbing strong fillings to Stein ones. So just to recall the contact structures classification on lens spaces, Honda and Giroux proved that all tight contact structures on lens spaces, there's a typo there, are given by Legendrian surgery on a linear chain of Legendrian unknots. And they're all strongly fillable. In fact, as we just mentioned, they're all Stein fillable. So an example of this is, let's look at L13-8. So how you would get the linear chain of unknots is you expand 13-8 or negative 13 over 8 in a continued fractions expansion as so, and then you get Legendrian unknots, and you get a link of Legendrian unknots where each component has as many cusps as the coefficient coming from the continued fraction expansion. And you get both universally tight and virtually over twisted lens spaces. The universally tight lens spaces are ones that, once pulled back to the universal cover S3, remains the tight structure on S3, whereas the virtually over twisted ones pull back to an over twisted structure on S3. The universally tight ones are all given by ones on which the stabilization seem to point in the same direction, whereas the virtually over twisted ones come from stabilizations pointing in different directions or from knots that are stabilized in either direction. So all lens spaces admit two universally tight contact structures, while the rest are virtually over-twisted. And while we do say there are two, these two contact structures are actually contactomorphic. So when we talk about fillings of contact structures or classifying fillings, we'll often say that there's one universally tight contact structure because all the results sort of follow automatically for the other universally tight structure as well. So the main result that we proved is, so this was proved joint with John Etnyre, and it was proven independently by Austin Christian and Leonin Lee as well, is that we give an algorithm to construct all symplectic fillings of virtually over-twisted lens spaces. And as a corollary to our result, or actually the result itself, the way it works out, it tells us that if you have a symplectic four-manifold that fills a virtually over-twisted lens space, then there exists a different symplectic structure on the same four-manifold that fills the universally tight lens space. So in some sense, if you have a list of all the four manifolds such that certain symplectic structures on them fill the universally tight structure, then you don't get anything new when you look at the virtually over-twisted ones. You might not get all of them for the virtually over-twisted ones, but you certainly won't get anything new. So that's an interesting outcome of this project. So to put it in context, what was known earlier about fillings of lens spaces is all universally tight lens spaces had their fillings classified by Liska around 2008, and fillings of certain classes of virtually over-twisted lens spaces, for example, for LP1s or LPM plus 1 plus 1, L plus M plus 1, or the lens spaces obtained by surgeries on two component chains, they were understood by work of Plamenevskaya, Van Horn Morris, America Lotti, and more recently Eduardo Fossati. So our work, so John Etnyre and my work, and also Christian and Lee's work completes the result because all the universally tight ones were known through Liska, and then we understand all the fillings of virtually over-twisted ones. The main techniques that were used to prove this theorem are, so the first one comes from a technique that was developed by Michael Menke, and the main result is that fillings of manifolds that contain a certain object called a mixed torus, or the containing mixed tori, can be obtained from fillings of smaller manifolds. And I'll talk more about this in a bit, but the idea is that if you have a manifold M that contains a mixed torus T, then you can sort of decompose along that torus to a simpler manifold M prime, and then the fillings of the smaller manifold, from those you can construct the fillings of M in a fairly standard way. So what this allows us to do is, given a virtually over-twisted lens space, you can sort of cut along mixed tori and reduce to some virtually over-twisted lens spaces whose fillings were understood by Liska. And so combining Menke's decomposition result with Liska's algorithm to construct and describe the fillings of universally tight lens spaces, we get an algorithm to describe and construct the fillings of virtually over-twisted lens spaces. So let's talk a bit about the techniques we use. Let's first talk about Menke's decomposition result. So I mentioned a mixed torus. So what's the definition of a mixed torus? So a torus in a contact manifold is called a mixed torus if it has a neighborhood that looks like T2 cross minus 1, 1, where T2 cross 0 is the torus we are looking at, and T2 cross minus 1, 0 is a positive basic slice, and T2 cross 0, 1 is a negative basic slice. Another way to say this is that T lives in a T2 cross I neighborhood built up of two basic slices such that the T2 cross I neighborhood is virtually over twisted. So they have opposite signs on each of them. So this is what a mixed torus is. And as I mentioned, the idea is if you have T living inside a manifold, which is a mixed torus, you cut the manifold along T to go from M to M prime, and then you create two torus boundary components and you cap them off with solid tori in a standard way that Menke describes in his paper, and you obtain a closed manifold M prime. M prime may or may not be connected. But so that's how you decompose from M to a simpler manifold in some sense, which is M prime. And so how it helps us understanding the fillings of M is that any symplectic filling of M is obtained by attaching a round symplectic one handle to a symplectic filling of M prime. So you have any filling of M prime, you attach what's called a round handle, and the whole thing gives you a filling of M. And all fillings of M are obtained exactly in this manner. Let us now revisit Liska's algorithm to describe the fillings of universally tight lens spaces. So for this, we need a few definitions. The first definition is that of a null sequence. A null sequence is a continued fraction whose value is 0. Just as an example, we'll say that 1, 1 is a null sequence because 1 minus 1 is 0. Another null sequence is 1, 2, 1. And there's a standard way to build larger null sequences from smaller one, which are called blow-ups that Liska describes in his paper. And topologically, that gives us this understanding that if you have a link of unknots on which you have the surgery coefficients coming from a null sequence by doing slam dunks, you can see that is exactly a description of doing zero surgery on the unknot, which is nothing but S1 cross S2, or on a more four-manifold setting, it's the boundary of S1 cross D3, which is going to be interesting for us. So, given that, now consider a rational number bigger than 1. If you're given a rational number bigger than 1, suppose it has it can be written as P over Q, then consider the continued fractions expansion of P over P minus Q. And suppose the entries in that fractions expansions are all non-negative integers, or all positive integers that are at least 2. Then we define this set ZPQ, which can be thought of as null sequences compatible with the pair PQ or the rational number P over Q, as all the null sequences such that Ni is less than or equal to Bi. Right? So a simple example can be if, say, your P over Q is just 4 over 1, then P over P minus Q is 4 over 3. 4 over 3 has the following continued fractions expansion. It can be written as 2 minus 1 over 2 minus 1 over 2. So the corresponding, so Z41 are the null sequences that have length 3 and all the entries are less than or equal to 2's, and there's 2 such null sequences, 1, 2, 1 and 2, 1, 2. and this is all. Right. So given that, we can now describe the fillings of universally tight LPQs according to the following algorithm. So suppose you're given LPQ and you have the universally tight contact structure on it and you want to understand its fillings. So what you first do is bring up the continued fractions expansions of P over P minus Q. Okay? And then for every null sequence that is compatible with PQ, you get a unique filling up to the diffeomorphism of LPQ universally tight. And how you build that filling is given by this description. So the above link in black, as we mentioned, since the surgery coefficients come from a null sequence, the link in black describes the boundary of S1 cross D3. And what you do is you attach two handles along the red, and you attach as many two handles as the difference between the corresponding BIs and NIs. And so Liska's theorem is essentially saying that all Stein fillings of the universally tight LPQ up to diffeomorphism are given by such constructions. You get a unique filling for each such null sequence, and other than this particular condition on P and Q, each null sequence gives you a different symplectic filling. Right. So with that as the background set up, let's now move on and try to understand the fillings of virtually over-twisted lens spaces. So let's first identify the mixed tori that show up in virtually over-twisted lens spaces. So as we mentioned, a virtually over-twisted lens space is described by a linear chain of unknots, and what you'll always see in them are stabilizations either going in different directions or knots that are stabilized in both directions, such as this. And so those are the regions where the mixed tori show up. So either in doubly stabilized components, this is where a mixed torus shows up, and if the direction of stabilization changes, then this is where the mixed torus shows up. And so given that, let's work out one example. So let's try and answer this question up to diffeomorphism equivalence. How many Stein fillings does the following lens space admit? And we're looking at L478, 175. So 478 over 175 admits the following continued fractions decomposition. So that allows us to understand how many cusps will be on each of these components. There'll be 6 components. And as you can see, it's clearly a virtually over-twisted 478, 175, because there's a doubly stabilized component, and also there's directions of stabilization changing, so it's virtually over-twisted. There's a number of mixed tori hanging about. So let's now try and count the fillings of this particular lens space. So by Menke, we'll first decompose the manifold along this, the mixed torus that shows up here. So the algorithm we describe, we first take out the doubly stabilized components, and then the M prime is the lens space given by this chain union the lens space given by this chain. So a filling of this lens space comes from a filling of the lens space described by the first two components, which is L11,4, and then a filling of the lens space described by these three components, which is an L13,5. So this is a universally tight 11,4, while this is a virtually over-twisted 13,5, because there's directions of stabilization change here. So we'll apply Menke's theorem again, but here the M prime is not uniquely obtained. There's different ways they can decompose. So you can either get a filling of these two and then attach a 2 handle along this, or you can remove this component and get these two lens spaces, which are L31 and L21, and attach a round 1 handle along this. So how do we now tell them apart? So recall that all the diffeomorphism types of the fillings are understood by the null sequences they correspond to. And so even these fillings are actually correspond to certain fillings of the universally tight lens spaces given by certain null sequences. So if we can identify which null sequences come up, then we can count exactly how many fillings that can show up. So a brief description of that is the following. So if you have P over Q equals 11 over 4, then the P over P minus Q continued fractions expansion is 2322. So that has two fillings that can come up. So that means that in this case, this universally tight part can have two fillings that can show up. Whereas for the 13.5 virtually over twisted part, the P over P minus Q sequence is given by 233. So a priori, the universally tight one on 13.5 can have two fillings corresponding to 212 and 121. But if we work through the fillings that come from L52 and then attaching a 2 handle, or the fillings of L31 and L21 and combining them, it turns out that both of them correspond to the null sequence 121. So there's actually a unique Stein filling for the virtually over twisted structure on L13.5. We give more details about how to combine these Stein fillings and the null sequence you get in proposition 2.22 of our paper. I'm also happy to talk about it in office hours if anyone wants more explanations. But the upshot is that once we get the null sequences for here and the null sequences coming from here, we can combine them to see that you get two Stein fillings of L478175, and they're given by these two null sequences, which is to say that the links that the manifolds that Liska described given by these null sequences, there are different symplectic structures on them that fill this particular virtually over twisted L478175, and that's all the fillings of this particular virtually over twisted lens space. All right, so I'll end my first talk here. Thank you very much for your attention, and I hope you join me for the second talk, where I talk about some very exciting applications to what we call the Legendre-Bergy conjecture, and also understanding cobordisms between lens spaces. Thanks.